In algebra, we have a property called the inverse property. And the inverse just simply means the opposite. So when you solve equations, you use this inverse property a lot because you know addition and subtraction are inverses, multiplication and division are inverses. But when we're dealing with functions, we're looking at letters. And so x and y are going to be inverses or opposites. So here's an exponential, and I'm going to write its inverse. X equals 10 to the y. Or I can write it as log base 10 x equals y, because the log is equal to the exponent. If you notice then, since this was the inverse, I just rewrote it here, and so these two are inverses of each other, or opposites. Doing the same for y equals e to the x. The inverse would be x equals e to the y. We don't like to have y in that position. We like to have y solved for. So I'm going to convert this into a form known as the log base e. And the log base e is now known as the natural log. And what we're saying here is that the exponent is equal to y. And so these are inverses. So what do inverses look like? Well, if you recall, graph of the log passed through this point 1, 0. It leveled out and continued to grow, but very slowly. And it had this asymptote. The exponential passes through the point 0, 1. If I was to put 0 in this position, I would get 1 out. So instead of landing on the x-axis, it lands on the y-axis. What happens here is that J-curve effect. So these graphs are what we call inverses of each other, where this is the exponential, and this is the log. So when I take logs, I'm undoing exponents. When I take a logarithm, I'm undoing that exponent by bringing it down in front. And there's a property about graphs that are inverses. That is, if this is a fold line, and that line is y equals x, the blue graph would fold directly upon the red graph. And that's what it means graphically to be an inverse. Exponentials and logarithms are inverses. They undo each other so we can find that unknown that's in the exponent position.